This is section 12.1, where we'll define and use sequences and series. A sequence is a function whose domain is the set of all consecutive integers. What we mean by domain are the values that represent the position of each term of our sequence. So you have your first term, your second term, your third term, your fourth term, and so forth. Those are considered to be the domain of our function. If a domain is not specified, it is understood to start with 1. Typically, we start with a 1 to represent our first term, a 2 to represent our second term, and so forth. The value of the range are called terms. The terms are the values that are in your sequence. So your first number, your second number, and your third number, they're all terms where the domain are the position. A finite sequence has a limited number. For example, 2, 4, 6, and 8, and it stops. There's no additional numbers. There's no ... to represent that it moves on. An infinite sequence continues without stopping. It goes on and on and on. 2, 4, 6, 8, 10, 12, 14, 16, ... It just keeps going on. Follows that pattern, on and on. The sequence can be specified by an equation that we often call a rule. For example, both sequences above are represented by, if this is our first term, our second term, third term, and fourth term, you get this term by saying 2 times 1. You get this term by saying 2 times 2. The third term by saying 2 times 3. So it's 2 times the position, and we like to call the position n, so we call it 2n. That would be the rule, 2n. Here we're going to write the first 6 terms using this rule. This is 2 to the power of n plus 1. So we're going to start out with the first term. So our n value is 1. Plus 1 tells us that this is going to be 2 squared, which is 4. Then we're going to have 2 plus 1, which is 2 to the third power, which is 8. 2 to the fourth power, which is 16. We get 32. 64, 2 to the 7th is 128. So we followed the rule to write out the first 6 terms of our sequence. It's just a list of numbers that follow that particular rule. Here's a different rule. This is 3n minus 7. So to figure out your first term, you're going to take your 3, times it by 1, and subtract 7. Gives us negative 4. To find your second term, we'll plug in a 2. 6 minus 7 is negative 1. To find our third term, we plug in our 3. Our fourth, we plug in a 4. And our fifth. So we have our sequence of numbers. -4, -1, 2, 5, 8, and 11. They're all following this pattern. If you notice, we're we're increasing by 3 every time. That's what this 3 would represent. And if we went down to a of 0, kind of like the y-intercept, it would actually be at the number -7. So here we're looking for a pattern. We notice this is the first term, the second term, the third, and the fourth term. Our pattern is square the position. So we get 1 squared, we get 2 squared, 3 squared, and 4 squared, and the ... means it would continue on and on. So our next term is going to be 5 squared. So our rule to figure it out, to figure out the nth term, whatever term you're looking for, you're going to square its position. The n stands for the position. In this case, two times 2 gives us 2. 2 times 2 gives us 4. We can also recognize that this is 4 minus 2. This is 6 minus 4. This is 8 minus 6. This was a test that we had learned earlier about an arithmetic sequence. So we can use our rule of a of n equals a of 1 plus d n minus 1. Some people like to use the concept of y equals mx plus b. That would work also. Our first term is clearly 2. Our difference we noticed by taking the term minus the one before it, and we saw that we had a common value that d equaled 2. By cleaning this up, we see that a of n equals 2n. In this case, if you take the 9 and divide it by the 1 before it, if you take the 27 and divide it by the 1 before it, take the 81 and divide it by the number before it, we get this common ratio of -3. So this is considered what we had learned in an earlier lesson, geometric. It has its own format of the first term times a ratio n minus 1. So our first term is -3. Our ratio is -3 to the power of n minus 1. You could possibly leave it like this. That would be following our format. But because the bases are the same, and this has an exponent of 1, if the bases are the same, you add exponents. So 1 plus n minus 1 could actually give you -3 to the n power. Looking here, we have our first term, second term, third, fourth, and fifth. Fifth, I guess, would be out here. The pattern, what's happening? The denominator is the position squared. So our next term is going to be 1 over the fifth term squared. So what's happening here, to find your rule It's 1 over your position squared. So not quite as involved as if we have arithmetic or geometric. Sometimes these can actually be easier. Sometimes they're pretty tricky to work with. Here we notice we're going up by 2. We're going up by 2 and 2. So we're going to say 5 minus 3, 7 minus 5, 9 minus 7. Each time we get this common number of 2. So our difference is 2. That tells us it's arithmetic. And we're going to start out with a of n. Our first term is 3 plus our common difference, n minus 1. Distributed through. So we get a of n equals 2n. 3 and a negative 2 gives us a positive 1. So that's our rule for this sequence of numbers. First term, second term, third, and fourth. Notice how the denominator is changing every time, but the numerator is staying the same. The denominator is the position cubed. So to figure out your fifth term, it's going to be 1 over 125. And our rule (1 over n cubed).